Hello everybody, thank you so much for having me. My name is Cassandra Miller, and today I'm going to be telling you about our work, Quantitative ex vivo imaging of actinium-225 with the iQID alpha camera. So, the activity distribution of a radiopharmaceutical within tissue is often assumed to be homogeneous, for example, sometimes during PET or SPECT imaging for dosimetry, and this is known to be untrue. Tumors or other tissues may have necrotic regions, or regions of very high uptake due to vascularity and other factors. And the field of tumor heterogeneity is not very well understood at this time. However, learning more about it could provide exciting insights into radiopharmaceutical therapies, particularly if it can be correlated with therapeutic outcomes. Now, beyond just the qualitative tumor heterogeneity, quantitative measures such as the intertissue activity distribution and the absorbed dose distribution of a radiopharmaceutical would be particularly interesting. And this is especially true for pharmaceuticals labeled with isotopes like actinium-225 and other alpha emitters, which are much more poorly understood compared to beta emitters, for example, due to the extremely short range of alpha particles, which requires analysis on a very small scale. Now, the ionizing radiation quantum imaging detector, or iQID camera, is a scintillation-based detector that is able to image alpha particles ex vivo. For example, those emitted from tissue sections of mice injected with an alpha-emitting radiopharmaceutical such as actinium-225, and this is an image of the camera here. Images from the iQID camera are initially qualitative. In this image here, we have the intratumoral distribution of an actinium-225 labeled antibody in a mouse tissue section. And this image already is very interesting. You can see that there is a very heterogeneous distribution within the tumor. However, the image is just in units of counts, so all we know is how many alpha particles were emitted in each region. What would be very valuable to us is to obtain some quantitative measures, such as the activity distribution and the dose rate map, especially if we would be able to correlate those variables with things such as the injected activity and even the therapeutic outcome. And to this end, the aim of this work is to generate quantitative images with the iQID camera that would enable us to perform microdosimetry studies. So we began by calibrating our camera. In order to do this, small drops of actinium-225 dissolved in phosphate buffered saline were pipetted onto a zinc sulfide scintillator and imaged with the iQID detector for 24 to 46 hours. The activities range from 0.8 to 60 becquerels, and we confirmed these activities using gamma spectroscopy, and we imaged 3 dots of each activity. On the left, you can see the dots on the scintillator on the camera. We outline the dots using a wax pencil to prevent the dots from spreading out, and in the middle, we have an image from iQID of the dots. The dots aren't perfect, but they're delineated enough for us to create ROIs. And we chose our camera settings based on settings that gave us appropriate images of tissue. All of the images of our dots were segmented, and a calibration factor was determined by generating a calibration curve and performing a linear fit. And this will allow us to obtain a calibration factor in units of counts per second per becquerel. Now, because our iQID image is in units of counts, and we know the scan time of our images, this will allow us to convert our image from units of counts to units of activity, which is becquerels, and therefore obtain an activity distribution map. So here is an image of our calibration curve and the corresponding linear fit. The y-axis of these plots is in units of counts per second, and the x-axis is in units of activity. And we obtained a calibration factor of 3.54 times 10 to the negative 4 counts per second per becquerel. So once we obtain an organ image, we can divide that by the scan time in seconds to get units of counts per second, and then divide that by this calibration factor to obtain an image in becquerels. So that is how we can obtain an activity distribution. However, if we would like to take this one step further and also obtain a dose rate map, it will require the use of a dose kernel, which we created using simulations. We used Gate version 9 Monte Carlo software and simulated a point source of actinium-225 in the center of a two-dimensional box with the same density of water. And the pixel size of our dose kernel was identical to the iQID camera, being 19.53 micrometers. Now, once we have this kernel, which you can see in the bottom left, we can convolve it with our activity map, and this will provide a dose rate map within the organ slice in units of milligray per second. Before we can obtain an activity distribution and a dose rate map, we first need an image of an animal tissue. So a tumor-bearing mouse was injected with 20 kilobecquerel of an actinium-225 labeled antibody. Around 7 days after injection, the mouse was sacrificed. A spleen was collected, frozen, sliced into 14 micrometer thick slices, and imaged with the iQID camera for 120 hours, 16 days after collection. And in this image on the right, you can see 3 of the mouse spleen slices on top of the scintillator paper on top of the camera. And here is the image we obtained from the iQID detector of one of the mouse spleen slices in units of counts. So here you can see the actinium-225 labeled antibody distribution within the spleen. And it is very heterogeneous, as we would expect, with areas of low to no uptake throughout the spleen. Using our calibration factor, we can now convert our iQID image from units of counts to units of becquerel, which you can see on the right. Our image hasn't fundamentally changed, only the pixel values have, but we've changed the color map just to make the two images easier to differentiate. Now we also decay corrected our activity image to account for the delays in imaging time. Because we imaged 16 days after collection, we decay corrected by 16 days. So the activities in this image will match the activities in the mouse spleen the day that the mouse was sacrificed. Now our activity is somewhat small. It looks like it's on average about 0.10 becquerel, but this is what we expected because our slice of spleen is so small, only 14 micrometers. So now, using our dose kernel, we can convert our activity distribution map to a dose rate map, which you can see here. Based on this image, the average dose rate within the mouse spleen is around 2 to 4 milligray per second, with some regions of much higher dose and some regions of low to zero dose. So in conclusion, it is possible to generate quantitative images of the actinium-225 activity distribution within mouse tissue sections using the iQID detector. Here we looked at the activity distribution and the dose rate distribution, but a lot of other variables are possible as well. And the future goals in this work are to find the activity and dose distributions for more tissue sections with different pharmaceuticals, in particular tumors, which we didn't get a chance to look at today, but we would like to in the future. And the long-term goal here is to find correlations between the dose rate, degree of tumor heterogeneity, with the therapeutic efficacy and other biological variables. So thank you everyone for listening. Please feel free to contact me if you have any questions. Thank you.